For this recording, we're going to be factoring special forms. And by special forms, what I mean is there are some types of polynomials that have like patterns involved. And once you know what the patterns are, there's kind of a formula that you can remember. And then it's faster for you to factor them than the good old-fashioned way. One of them is this, which is the difference of squares. And it's exactly what it sounds like. You're subtracting two squares. So both of these can be any kind of square. 9x squared minus 9, so on and so forth. This all works as long as both of these are perfect squares. And perfect squares are just those numbers that you multiply together to get, or you can take the square root of and it comes out even. So like 49, 64, 81, so on and so forth. Alright, so the rule for this one is, you know that you're always going to start with two sets of parentheses. And the first part of the parenthesis is whatever the square of the first term is. And then the back part is the square of it. Or the square root, I should say. And then for the difference, we put a plus and a minus. Now the reason you do this is because when you FOIL this, your middle term will be plus 2x and minus 2x. So it cancels out, which is what we want here. Notice there is no middle term. It's just your first term and your constant at the end. So that's why that we have the plus and the minus. So the rule is you take the square root of the first term, the square root of the last term, and then you put a plus and a minus between them. So another example would be this, and this is 4.6 out of your book, which I'm on page 453. Alright, so this is a perfect square and this is a perfect square, and we're subtracting, so it's the difference of squares. So we know we're going to have two parentheses. We're going to find the square root of this, and that goes in the front part of the parenthesis, and then find the square root of the last, and then we need to put a plus and a minus in between. And another example, perfect squares that we're subtracting. So we'll put an x in our first, the square of the first, square root of the first, and the square root of the last, on a plus and a minus. And then our final answer. Now let me change this. Let's say the question was this. So again, find the square root, and a square root, and a square root, and a square root, and a plus and a minus. When I do this, this is still the difference of squares. It's still a perfect square for our two terms. So we want to take this one more step. So remember, this is x, and 3, and a plus and a minus, or a minus and a plus. And then we also have this. Now there is no such thing as the sum of squares, so this cannot be factored any further than what you see. So this is our final answer. Let's see if I can find another example. Let's do 25x squared minus 4y squared. So first thing I notice, and always when you do these, when it asks you to factor, is to look to make sure nothing can come out of both terms before you begin, because that makes things so much easier. Alright, so neither one have anything in common, so I notice this is a perfect square, this is a perfect square. Alright, so we take the square root of this, and the square root of this, and then a plus and a minus. Neither one of those can be factored any further. Let's see what else we have. Alright, we also have another special form, and it's called the sum and difference of cubes. and this would be one example. So when I look at this, this is a perfect cube and this is a perfect cube. Cube meaning I can take a number and multiply it times itself 3 times and it comes out perfect. So this, if I take the cube root of it, that would be 2. If I take the cube root of this, it would be x. So now we have a formula, however. Alright, so I'll kind of show you where it comes from. So take the cube root of this and the cube root of this, and we put a plus in there. Then to figure out what goes in the other set of parentheses, we square our first, we multiply these two together, and we square this. Now when we do that, we have to worry about our signs. This one is minus and this one is plus. So this is the rule for the sum of cubes, plus minus plus, and it always works if you just remember the formula. If not, let's say you kind of get in a jam and you can't remember if it's minus or plus. After you write it, kind of distribute and FOIL it real quick and see if you get rid of that middle term. That's usually what we have to have, a minus in there somewhere to get rid of that middle term. So let's do another one of those. So 2 sets of parentheses. Our first set of parentheses is the cube root of the first term, which they call a, and this is called b. So the cube root of 27 would be 3. There's always a plus in between there. Then we square our first term, multiply the 2 terms, square our last term. And I prematurely put a plus in there. And then remember, it's plus minus plus. We also have that was the sum of cubes. We also have the difference of cubes. So there's an example. And the only thing that is different on the difference of cubes is where your plus and minuses go. Alright, so this time, same thing, cube root, but this time we have a minus here. And then we do the same thing as we did before. Square our first term, multiply our 2 terms, square the last term. And then this time we have pluses in the middle. So really that is the only difference between the two. Is here we have a plus, minus, plus. This we have a minus, plus, plus. We could do y to the third minus 1. Perfect cube. 1 is always a perfect cube, perfect square, perfect anything. So we have 2 sets of parentheses. Cube root of y is y. I'm sorry, cube root of y to the third is y. Cube root of 1 is 1. Minus goes in the first one. Then we're going to square the first term, multiply the 2 terms, square our last term, and then put pluses in there. We can change it to a plus. Cube root of y, cube root of 1. This time the plus goes in the middle of the first one. Square, multiply, multiply, and then it's a minus and a plus. Alright, if you have any questions, let me know.